Welcome to the University of North Dakota's introductory training for flight operations at high-elevation airports. At the conclusion of today's session, you should understand the dangers of aircraft operations at high-elevation airports, the importance of regulation and training regarding high-elevation airport operations, and how managed use of oxygen can prevent hypoxia and its consequences. While wearing an oxygen mask for regulatory compliance is likely nothing new, today you will have the unique opportunity to learn how oxygen can protect you from the very real dangers of hypoxia, the silent killer. Hypoxia is a condition in which the body is deprived of adequate oxygen supply at the tissue level. Hypoxia may affect the whole body or just a localized region. When the brain is starved of oxygen, symptoms can range from short-term dizziness or concentration problems to severe long-term issues including loss of vision, speech, and memory. If the hypoxia is mild, there will be problems with concentration, attention, coordination, and short-term memory. There may be headache, lightheadedness, dizziness, an increase in breathing rate, and sweating. There can also be a restriction in the field of vision, a sensation of numbness, or tingling and feelings of euphoria. As the degree of hypoxia becomes more pronounced, confusion, agitation, or drowsiness appear, along with a bluish tinge to the skin, often most apparent around the lips, mouth, and fingertips. There may be brief jerks of the limbs, seizures, and if it is severe, it will result in loss of consciousness and coma. The risk of hypoxia exists for the flight crews of both non-pressurized and pressurized aircraft. Pilots of non-pressurized aircraft landing at an airport above 8,000 feet MSL may need to don an oxygen mask long before approach and landing. The same applies to pilots of pressurized aircraft, since the plane will have to depressurize at some point in the arrival phase in order for it to land depressurized. Globally, there are 46 airports above 8,000 feet MSL, with 24 residing over 10,000 feet in elevation. Every day, 42,000 flights and 2.5 million airline passengers cross more than 29 million miles of airspace. Each day, an average of 21,000 passengers fly in or out of just 10 of the world's high-elevation airports. Obviously, the need to standardize high-elevation airport operations is of paramount importance. Oxygen planning and management is necessary to remain within the safe operating parameters of any safety management system program. The focus of today's introductory training chamber ride will be the recognition and mitigation of slow-onset hypoxia. There are multiple types of hypoxia, one of them being Histoxic Hypoxia, also called Histotoxic Hypoxia. This is the inability of cells to take up or use oxygen from the bloodstream, despite physiologically normal delivery of oxygen to the tissues. To the pilot, this means that even though there is an adequate supply of oxygen to breathe, and although oxygen is being circulated by the blood, the cells are unable to accept or use the oxygen to support metabolism. While hypoxia from high-elevation airport operations gets little publicity, alcohol and narcotics are two of the well-known factors that cause hypoxia. Much can be learned by examining regulations regarding alcohol use, which is highly controlled and regulated in the airline industry. While 0.08% blood alcohol concentration is the legal limit for operating a vehicle in the United States, the FAA mandates a blood alcohol level of 0.04% or less for operating an aircraft. Some airlines will tolerate only 0.02%, and in some countries there is a zero tolerance for any alcohol in a pilot's bloodstream. Operating an aircraft under the influence is an automatic revocation of the pilot's license and the tragic end of his or her livelihood. So while we are discussing alcohol, which can be identified in a person's bloodstream, the real issue here is how hypoxia displaces oxygen to the brain and the resulting reduction of cognitive abilities. Fatigue can also display similar symptoms to hypoxia, along with the same reduction in cognitive abilities. Like alcohol, sleep exhaustion slows reaction time, decreases awareness, impairs judgment, and increases your risk of crashing. The U.S. National Highway Traffic Safety Administration reports that drowsy driving is related to at least 100,000 motor vehicle crashes and more than 1,500 deaths per year. This is just from fatigued driving, not actually falling asleep at the wheel. Some studies show that fatigue can be as serious as driving under the influence of alcohol. One study shows that moderate sleep deprivation produces impairments equivalent to those of alcohol intoxication. After 17 to 19 hours without sleep, performance was equivalent or worse than that of a blood alcohol concentration of 0.05%. After longer periods without sleep, performance reached levels equivalent to a blood alcohol concentration of 0.1%. Most states set their DUI limits at 0.08% for those over the age of 21. The average legal limit for commercial drivers is a BAC of 0.04%. If we convert these blood alcohol concentration percentages to their fatigue performance equivalents, skipping 1 day's sleep already makes for unsafe conditions. In recent years, fatigue rules have been created in FAR 117 to mitigate the hazards of not having enough sleep. These rules are extremely comprehensive and place a significant burden of risk on the pilot, since it is the individual that must manage his or her own body. Violation of these rules can result in revocation or loss of license for the pilot. Alcohol use and fatigue are two highly regulated situations which can abruptly end one's professional flying career if not properly managed. Next, let's examine a less recognized but equally dangerous situation, where cognitive bandwidth can be severely compromised. The common thread between alcohol use, fatigue, and hypoxia caused by high-elevation airport operations is the loss of one's cognitive ability and impaired situational awareness. Flying under the influence or flying while fatigued both carry stiff penalties for pilots. Even though there is no legal ramifications for the management and prevention of slow-onset hypoxia due to high-elevation flight operations, the importance of managing this hazard is equal to or even greater than the other two. The solutions to cognitive impairment caused by alcohol or fatigue are obvious: not having a drink and getting enough sleep. Slow-onset hypoxia is insidious and can go undetected if not properly trained for. Planning for the risk, recognizing early symptoms, and knowing when to use supplemental oxygen are crucial skills. What should be clear by now is that high-elevation, slow-onset hypoxia must be managed, since the outcome will have the same disabling hypoxic effect as alcohol abuse and fatigue. Flight crews are faced with a twofold challenge: remaining within the legal boundaries as defined by regulation, and remaining cognitively unimpaired due to lack of oxygen. Until now, little to no guidance has been available on the prevention of slow-onset hypoxia during flight operations in high-elevation airports. Current regulations outline procedures in flight as it pertains to cabin pressure altitudes, but there is little direction to help manage oxygen requirements when elevation of the airport is above 10,000 feet. For example, Title 14 CFR 121.327 and 121.329 state that oxygen must be used at all times above a cabin pressure altitude of 10,000 feet. This raises many questions. What part of a flight or pre-flight denotes when the pilot is in command of the aircraft and must comply with regulation? What if the crew has an extended layover and will spend the night at high elevation? Is oxygen required the entire time? Specifically, what if the so-called cabin pressure is above 10,000 feet and the aircraft and crew are standing on terra firma? Another example of the need for guidance and regulation would be a flight crew flying from a low-elevation airport into a high-elevation airport. The pilot would depart the low-elevation airport using normal and well-understood procedures defined by regulation. The pilot would know that when the cabin altitude exceeds a certain value, oxygen use would be required. So far, so good. However, in order for the aircraft to be depressurized for landing, the flight crew would need to know at what cabin altitude should they don their oxygen masks. When after landing can they stop breathing supplemental oxygen? It is impossible to predict exactly when, where, or how hypoxic reactions will occur in an individual pilot. The appearance and severity of the signs and symptoms are aggravated by several factors: rate of ascent, time spent at altitude, physical activity at altitude, fatigue, self-imposed stress, extreme ambient temperature, and individual physiological fitness. Unfortunately, our industry has not had much information to answer these questions raised by these scenarios. SAE International creates standards which are internationally recognized for their role in helping ensure the safety, quality, and effectiveness of products and services across the mobility engineering industry. The organization's aerospace group is in the final stages of approving SAE ARP 6527, Oxygen Considerations for Flight into a High Elevation Airport. To date, it is the only comprehensive document of its kind and will be referenced multiple times throughout this training module. Information provided in SAE ARP 6527 will provide a basic framework for hypoxia avoidance and oxygen management so that the operator can develop an SMS-compliant procedure that is essential for protecting crews and their passengers. Guidelines and programs like these are being developed to meet the standards of the aviation industry and to establish safe procedures into a very harsh and unforgiving environment. Today's introductory training for flight into high-elevation airports will highlight the areas of importance and provide solutions in which pilots can successfully and safely manage their flight into these extremes. Since hypoxia is extremely subjective, it is imperative that flight crews become aware of their personal subtleties in a controlled environment. When these hypoxic markers are recognized, it will signal crew members to immediately don their oxygen masks to mitigate these effects. Training to react to these hypoxic markers will be an essential part of this course. The training is designed to provide guidance, limit flight deck confusion, reduce pilot task saturation, encourage personal recognition of hypoxia, and then mitigate the associated risks through the use of oxygen. This training will also introduce new technology which reduces task saturation, so flight crews can remain focused on normal departure activities. So once again, welcome to today's training, Safe Operations into and out of High Elevation Airports.